number 6.
Yes.
Set. Okay. So the reporter has 5 minutes to prepare. Okay, 5 minutes to prepare. And also please write your name. Reporter, opponent, and reviewer. Please write your name.
So we don't know it's weight check, right? Okay. This one? Seal. Okay. Sorry, is anyone missing their laser pointer? Sorry, that's okay. You have 2? What? So, which team also lose their...
Okay, reporter takes the floor.
Honorable judges and worthy observers, I'm the reporter from TYPT. Today, I'm going to report problem number 6, dripping faucet. So, starting from the problem statement, a leaky faucet develops interesting dripping patterns, where the time between the drops depends on water flow rate. Investigate this phenomenon and study how it depends on relevant parameters. We are focusing on the patterns of drop rates, surface tension, and oscillation. So, about the phenomenon, when the water is flowing at a very small flow rate, the intervals between the drop is in a single period phase, which means that the intervals between the drop only has one time. However, if we slightly increase the flow rate, the system enters the double period phase, which means that there might be 2 types or 4 types or 8 types of intervals. And thus, when the flow rate is large enough, the system becomes unpredictable. So this is our theoretical model. We use the mass spring damper model. A drop suspended from a tube is pulled upward by surface tension force and vicious force, and it is pulled downward by its weight. In this equation, K is a spring constant due to tension. However, K is dependent on mass, while gamma is a damping coefficient due to viscosity. According to the Rayleigh formula, a mass of water coming out of a tube of radius r can be given by this equation. And so by approximating the function to 3.8, we can obtain equation 1. Also, the surface tension can be calculated by the size of the droplets. So we use Young-Laplace equation, and we can get equation 4. And by substituting R1 and R2, we can get equation 6. When Z is at the point where the width of the drop is the largest, we can get R equals R2 and equals R0, and we can get equation 7. And by substituting the found number into our equation, we can get equation 8. And we use R0 as a unit of length, and we get equation 9. Finally, by approximating the found number as a function of BS divided by BE, we can get the final equation where A equals to 0.345 and B equals to minus 2.5. Here's our observation and assumption. So we observe satellite drop when the flow rate is large enough. So to simplify the model, we assume that the shape of the water drop is half sphere or half ellipsoid after the rebound and before the napkin. This is our experiment setup. So we use the rod to stabilize the barrette, and the barrette is connected with a tube, and at the end of the tube, we use string and tape to stabilize it. In our preliminary experiment, we determine the surface tension and the density of slow water by using the equation we mentioned before. And we also determine the mass of the water drop using 3 different ways: by directly collect the water drop, or find the volume in the slow motion medium and times it by its density. We also calculate by Rayleigh formula. And here are the results of the mass of water drop. In our first experiment, we want to investigate the relationship between drop rates and flow rates and different radius of tube. And relevant parameters include water flow rate and radius of tube, which is small, medium, and large. So for each group of experiment, we plot the interval versus drop stress to observe the pattern. And we also plot the return map and to see whether there is pattern. And this is for the single period phase. And this one is for the double period phase. And this one is also in the double period phase, however, it has 4 intervals. And when the flow rate is large enough, there is no clear pattern on the drop versus intervals map. However, the slight symmetry of the return map might indicate underlying structure. And for medium cube, we did similar experiment. And this is the single period phase, the double period phase, and the more complex a more complex or unpredictable pattern. In our experiment 2, we want to compare the drop rate between water and salt water. And for radius of tube, we have used medium and large tube. And for liquid, we use water and salt water. So this one is a single period phase where both the flow rate of water and salt water is approximately 0.2 millimeters per second. And this is a return map. And this is the double period phase where both water and salt water is at flow rate approximately to 0.29 millimeters per second. And this is a return map for the double period phase. When the flow rate is larger or approximately to 0.3 milliliters per second, the salt water flowing turns from water drops to a water jet. However, pure water still remains as a water drop with a flow rate of 0.35 milliliters per second. So this experiment shows that a liquid of lower density forms the water jet more easily. And this is our result. So from this graph, you can see that the intervals of the salt water is always smaller than the intervals between the drop of pure water. And this can be explained by the formula we mentioned earlier, because the surface tension of salt water is smaller. So the mass of water drop it produced is also smaller. So it requires lesser time to form the water drop and similar flow rate. We also observed that in similar situation and with similar flow rates, the value of intervals of water drop divided by intervals of salt water has a similar value. For example, it is about 2.1. And we also conduct similar experiment with large tube. And here is the double period phase with flow rate approximately to 0.4 millimeters per second. And this is a return map. And this one is for 0.5 millimeter per second. And this is a return map. And by collecting the data, we can observe similar results. The intervals between the drop of salt water is always smaller than the intervals between the drop of water. And similar to the previous experiment, we observed that in similar situation in similar flow rates, the value of the intervals of average intervals of water divided by salt water has similar value. In our final experiment, we want to investigate the oscillation of water drop. So here's some relevant parameters. So we use 4 different flow rates, and for tube we use medium, and for liquid we only use water. So according to the theoretical model we mentioned before, this model shows that the dripping faucet is a damped oscillator. And this graph is obtained by tracking the bottom of the drop, and we divided it into 4 different parts. The first part is the oscillation due to returns, and the second part is damped oscillation, and next, and finally, the water drop flows. In this experiment, we are only focused on this part because we assume that in this part, the shape of water drop is either half sphere or half ellipsoid, so it is easier to determine the mass center. To analyze the oscillation, we fit the midpoint with polynomial equation and assume that the displacement given by the equation y indicates the equilibrium position, and y minus y follows the equation of the oscillator, which is equation 12. And because the mr dt, which is a constant, is very small, so we assume that this term is negligible. And the motion equation of the damped oscillator is shown in equation 13. We also assume that the angular frequency omega is linearly dependent on time. So to verify that, we first find the maximum and minimum displacement. So the maximum and minimum displacement occurs in cosine function, where the angle is integer multiple of pi. And by solving the equation, we can observe that the relationship between t and n is quadratic, and it is consistent with our experiment result. So we use the theoretical model. We fit the trajectory of the water drop. And this one is for 0.11 millimeter per second. And the next one for 0.15 millimeters per second. And next for 0.26 millimeters per second. And finally for 0.635 millimeter per second. So by using the data, we observe that larger flow rate corresponds to larger amplitude. Also, when the flow rate is larger, the initial angular frequency is smaller. The formula has similar damping coefficient, similar to the theoretical model, where gamma is a constant. Here's our conclusion. First, the larger the radius of the tube is, the larger flow rate is required to reach the same condition. Also, some water produces water drop of smaller mass. Therefore, in similar flow rates, the intervals of the water is smaller than those of pure water. Third, as the flow rate increases, the water droplet oscillates in large amplitude, smaller initial frequency. However, the damping coefficient doesn't change according to flow rates. Here are some possible deviation. First, the video frame is 240 frames per second, so the data might not be precise enough. Next, although water is added to the burgers constantly, there is still slight pressure differences, which might influence the flow rates. For our future research, we hope that we can use different liquid with similar surface tension to water, but with different viscosity to analyze the influence of viscosity on water droplets.
Okay, time's up, and the opponent has a question.
So, for your experiment, did you put the soap water into the tube, which then was measured with the flow rate of that?
Please protect your voice.
Yes.
Why do you think a mass spring model is the best model for this experiment?
Because the water drop is mainly dragged upwards by surface tension force, and the surface tension force can be seen as similar to a spring, while the vicious force is similar to a damping.
For your experimental setup, where did you supply the water that allowed you to get it into the tube?
So we just added from the top because
So you use a tap, and then the tap was connected to a tube, which then you measured the water flow rate.
so we use a ferret and connect it with the tube.
Do you have any diagram to show that?
This one.
So the tube is, none of the fluid is exposed to here except when you release the valve. Is that correct?
Yes, the tube is filled with water.
Did you do anything to make sure, or use a siphon that made sure the water flow is constant as it left the tap and went into the valve?
We try to maintain the flow rate by constantly adding the water to the ferrets, so that there is so to minimize the pressure differences.
Okay, thank you.
Okay, so the opponent, 3 minutes to prepare.
in the opponent for no lighters, and I'm going to be opposing the topic number 6, dripping faucet. So first of all, let's start with the problem statement, which is a faucet. A leaky faucet develops interesting dripping patterns where the time between the drops depends on the water flow rate. Investigate this phenomenon and study how it depends on relevant parameters. So the ideal structure of investigation is to use a mass-free model. Set up the faucet connected to a valve, which is then connected to which is used for a siphon. And then you have uniform drops of water through the valve. Then you use a laser to measure the time interval as the water is dropping. So the purported structure of solving the phenomenon. So first they analyze the phenomenon. They use the flow rate to separate like the intervals, and then for the model of the behavior, the drops, they use like drop spring formula, chemical formula, and the Rayleigh formula plus Young's Love-Place formula to calculate the radius. And then they also assume that the droplets are spherical. And then lastly, they compare the behaviors. So they measure the volume of water in 3 different ways. And then they plot the flow rate versus the period to return like the map. And then they found a predictable state. Then they analyze the oscillation. And then their main focus for this problem statement is the patterns of the drop rate, the surface tension, and the oscillation, which is due to the mass spring model. So some pros and cons of the report is pros. The reporter had a clear voice. She tested many cases, which generated a lot of return maps, and she showcased the surface tension's relationship to the radius with adequate calculations. But a few cons are there's many observations, so the connection to the theory was unclear, and therefore the return maps was not as clear and as sufficient as we would want. And then the relationship between the flow rate and the amplitude was not really clear either. Another con is that the reporter did not include slide numbers for the slides, so we couldn't determine which slide included what information. And then lastly, the axis title could be larger and more visible. So here are my points of discussion. First of all, I would like to invite the reporter up to discuss.
Okay, so time to discussion.
Okay, so I would like to question your parameters. So first of all, you use a tube, and as shown in one of your slides, which does not have page numbers, so could you go to the slide that shows your experimental diagram?
Which experiment do you want?
The one where you showed a photo of the experiment. This one. So for the tube, as you can see, it's not, the tube goes from the side into the string and the tape, and therefore the direction of the flow rate, even though it's constant, it's not directly vertical, so therefore as the water is being pumped out, the pressure inside of the tube is not constant. But do you have like any justification to this?
Yes, so we try to make it as vertical as possible. So that's why we use string and tape, because we want to make sure that this is nearly vertical when it's visible.
And why do you think using string and tape is a good, accurate representation to measure this phenomenon?
Because we need some distance between the tube and this one, so the water drop will not stick to the stick. So I have to use a string.
Did you have a valve that was open for you to allow the water to flow out?
When I open this, the water will go out.
So when you open the valve, as water is flowing out, the water travels through this tube, which then it changes in direction as it moves up the tube, which then changes the pressure within that's being exerted out. So For the next one is your parameters. So you use soap water, and because soap water, as you said that there's no air bubbles in the soap water. Could you justify for that?
I took out all the bubbles before I started experiment. And even if there is some small bubble, it will only appear on the top, so it will not go into the tube.
But as the fluid is traveling, air bubble accumulates as it travels upwards, because as you can see for experiment, as it travels, it does a curvature type of thing. So the air bubble, as you just said, it accumulates on the top. But is there no air bubbles accumulating on the top of the second curve? Because that's also where the density is high, right?
Oh, there is no air bubble anywhere from here to here.
And also, when you measure the volume inside of your volume measurement thing, is that? Yeah. When you measure the volume of the fluid, how did you do this procedure? Because for a soap water type of experiment, you would then, as the water is being dropped into this cup, there's going to be a lot of bubbles that then come out and accumulate, because you can't prevent that.
I don't observe the volume from this one. I observe from the top where there is some numbers, and because the water is the bubble is accumulated on the surface of water, so I just see the water level decrease.
So do you have any way you can show what numbers you're talking about, or what the top is attached to for you to measure?
Do you mean flow rates?
Yes, because you said you measured the water. You measured the water, the volume of the fluid. And do you have any justification or diagrams that show how you measured this measurement?
Yes. Just may I use the back?
Please, and project your voice.
So the flow rate is measured by seeing on the top, because there is some. So I just see how many seconds it should take to flow 1 millimeters or 0.1 millimeters.
So I believe you failed to mention that you measured the top, which is not shown in your diagram or any experimental photo in your reporter slide.
Yes, I didn't show this, but this is how I measure it.
So if you say you got rid of the air bubbles, how is that? How did you measure if in contact with the air?
Can you please repeat your question?
Because you said there is no air bubbles that go in, but as you measure the top, would there not be air bubbles accumulated from the soap that's accumulated on the top?
No, because it is here together. Because it looks like this. So I just observe this one. And this one is always very clear. Bubble will not go in. It just floats on the top.
Okay, and could you explain that as water is moving from here, is pressure exerting down on this tube? So there is pressure going in here, right? Atmospheric pressure, that pressure down. Then is there any justification for how this pressure affects the speed as it flows?
Yes. Because the flow rate can be determined by the height difference between this one and the one with you. So if as the water level goes down, the flow rate will decrease.
Did you account for this?
Yes. So I try to minimize the pressure differences by using a drop, and so to minimize the water that goes in. So I always add water on the side of the river. So the water will flow like this to minimize the fluctuation.
I believe you also failed to mention this part in your experimental procedure, how you use a dropper to keep the pressure constant. Is that correct?
Yes. currently a vacuum dropper because the water is slightly disturbed.
So as this water that's being dropped down, the water is being disturbed, right? Then how do you wait, but anyway. So you said you measured a set amount of water that drops through this system. Is that correct? You said it started from 1 milliliter to 0.5 milliliter.
No, this method is literal. So I just measure how many seconds it takes to zero to zero.
And then, okay. So as this water is being dropped through, you then connect it to this system, which then carries the water, right? As the liquid moves through the system, would the pressure velocity change for this fluid? Because I don't think they come into account as it's moving, the pressure is changing.
The pressure change is very small. So it's because the system is filled with water. So I don't think that this is. So I think it is. So I think because the flow rate is nearly constant when the pressure difference is not very large. So I think it is. It will not be big differences if we just measure.
Okay, could we go back to the... So you also said you used a mass free model to model your experiment, right? To model the oscillation. For the spring model, you did not account for the spring constant. How did you compensate for that?
The reason that I did not determine the spring constant because spring constant is dependent on the shape of the water and the mass of water, which is very complicated.
So you did not mention the spring constant using a spring model? Is that what you identified?
Yes, for this model, I will just using it to fit the final experiment to observe the amplitude and the angular frequency.
So if you use the spring model to model the experiment and measure the amplitude, how did you do the calculations without including the basic spring constant that is the hook for the spring model?
Because in our last experiment, K is related to angular frequency, and I assume that the angular frequency is linearly dependent on time. So I cannot use K in my last experiment.
And also for your error bars, you had error bars for the soap one, but you failed to put error bars into the water one. Is there an explanation for this? When you put error bars into your soap experiment but not the water one, why is that?
Because our experiment doesn't need error bars, and because the one with soap and water, we want to compare.
Okay, time's up. So for the opponent to summarize the discussion.
So to summarize the discussion, we discussed the tube usage. So first of all, the tube isn't directly vertical, and therefore you can't control it. And then for the reporter, he said they used a string and a tape, and then that's their explanation. And then I recommended to use a rigid tip or a siphon. And then we also discussed the parameters, and what the release as soap bubbles makes it bad to use. And even though it's only an issue for the release part, it's also like sensitive. And then the reported states that the bubbles are small enough so it's negligible. And then we also talked about the experimental procedures. I also clarified the experimental procedures regarding the release of the droplets because they failed to do this. And also the mass spring model, how they didn't account for the
Okay,
spring
time's
constant.
up. The reviewer asks questions to the opponent and the review of the reporter.
Okay, first question.
gravitational force. Yeah.
There's no water pressure.
But the weight of the water contact.
Okay. How you control the radius of the drop mass?
What do you mean by the radius of the?
For next question. Tommy,
Okay, please raise your voice. Okay, raise your voice.
how many times you have tested vegetable and
Test.
experiment 3?
I tested many times. About 10 times. However, because some had some errors, so I just choose some that is the most easily to the best.
Okay. Okay, you both. The question is, as size smaller the drop, why the drop rate decrease? As the size of the drop becomes smaller, while the drop rate decrease.
Oh, do you mean the bubble water?
For next question.
Wait, I have an answer.
Oh,
I think it might be due to the Bernoulli's.
Okay, raise your voice. Raise your
It
voice.
might be due to the Bernoulli's principle.
okay. Is there a chart compared with the theoretical model?
Because for this experiment, we cannot determine the spring constant, so there is not many comparison between the theoretical and the experimental.
Okay, hands up. So the reviewer has 2 minutes to prepare. Okay, reviewer, takes the floor.
Okay. This is Clyde from Team Studio. Problem statement. A leaky leaky faucet development interesting dripping patterns where the time between drops depends on the water flow rate. Investigating this phenomenon and study how it depends on the relevant parameters. Okay, summary of the reporter. The theory and explanation. As the size of the drop becomes smaller, the drop rate increases. Reporter step by step get the result. And reporter count different mass of the water drop in experiment 1 and 2. About the experiment setup. The setup water drop, background paper, high-speed camera, and string tag, and they have different radius of the tube for 3.5 and 5. Okay, the reporter pros using tracker, which is a useful app, have tested tons of experiments. The discussion between the reporter and the opponent about the theory is lively. And they have clear picture about the experiment setup and drop rate. And did about 3 different types of tests. But about the cons, experiment 3 only use water to test it. And the tube and just like the opponent says, the exit title could be larger. And I think the reporter should speak more loudly. And our team thinks there's not enough photo for the whole setup. Summary the opponent. Asking about the flow rate. Talk deeply enough into the theory. Talk about the drop rate and surface tension. The opponent pros, I think, is a good suggestion of the question. Focus on the problem statement and also discuss the theory deeply and ask clearly about the page in this experiment. About the cons, maybe the sound can be higher because the opponent and reporter writing on the blackboard. So could be. Yes. Okay, and I think the opponent too early to start the discussion. And the bridge between reporter and the opponent is not enough. Okay, discussion about the experiment. Opponent asked about the setup, how you sure the water will go into the tube, and the reporter showed the picture clearly by lowering the pressure of the experiment or something. And I think the water drop starts at the hole of the dropper, and it's not easy to control the diameter of the water drop.
Oh, sorry. So then the reporter has 2 minutes to let this one prove reason why. Okay? Alright, so then time for question from the group. So any questions? Any questions?
Using their flow rate will increase the mass of the drop. When you increase the flow rate, and you think that they will be different from the drop mass or the drop value.
The mass won't change.
Sorry?
The mass won't change. It will just drop down faster.
Then
I think not. The the flow rate and the mass will cause something different, but I don't think.
I also don't think so because the mass only affects the velocity of the fluid.
Okay, then time for grading. Or more, okay, one more question. Okay, yes, time.
for the reporting, because I didn't get the point about the oscillation. What you mean the oscillation?
Because when the water drop is falling down, it will oscillate as the mass increases. It will oscillate.
So how do you measure the oscillation of the drop?
I measure the oscillation of the drop by first fitting the trajectory, and I assume that the trajectory gives the equilibrium position. So then I make and along the trajectory will gradually decrease. But to analyze it, I make it smooth like this, so it is easier to observe the amplitude and the frequency.
Let's get the point in the oscillation is before the drop or it is still on the tube and it oscillates.
Here's the so you can see before the length of the drop increase dynamically, this will oscillate like this.
Okay, so the oscillation is still on the tube. So the radius of the drop is oscillating.
Yes.
Okay.
Okay, no more question, we will grading. number for the reporters. Four, 7, 6, 7, 5. Okay. And number for the opponent. 3, 7, 6, 6, 5. And number for the reviewer. 3, 5, 4, 4, 5. Okay, so comment for the reporter. Okay, again, I give the lowest points. First of all, I don't see the evidence in your experiment presentation. There's couple period, 4 period. I don't see any evidence. And you throw out a lot of equations, and then it's hard for me to connect your equations to your experiment. The radius, there's no picture to show how you measure the radius, and so the whole presentation basically to me is a lot of numbers. And for numbers, there is something called scientific notation. You don't put 8 zeros in front of your digit. And there's no way you can measure precision down to 6 number to the actual decimal point. So look at your presentation. A lot of it have a 6-digit after decimal points. Okay, that reflects to me the data you measure since we've already get. So, okay, it's your responsibility to make your presentation convincing and clear enough to your audience. Okay, and for the highest points, Professor Fong or Professor Tom?
Yeah, I think you could do the manual of the experiment to try to figure out this phenomenon. But for the maybe you can try to improve how to present your experiment data because there are so many, so it's hard to get the end point actually. And just like I think Professor Khan is right that it's important you show effective resolution for the instrument when you do the measurement.
Okay, Professor Fong? Comments? Okay, no. Comment to the opponent, again I give the lowest point, is the test about period between the drops or the flow rate. Can we look at the statement of flow rate?
The time period
Between the drops, not flow rate.
on
Okay, but the whole discussion is flow rate. We discuss how it will with or without bubble and all that. I think it's the point. And other comments? The reporter's results show half of the time is how many period, how many types of period they observed, but there's no discussion about it. And this is the point. Okay, then coming for the reviewer, I think the viewer got the lowest point of all 3. So any comments? Okay, again, start from me. You give bullets, you have no sentences between what you present. You just say number one, number 2, number 3. The very few statements in between. Okay, so the reviewer is supposed to present what the reporter says and what the opponent says and how you think. But you basically just summarize and point by point, but no discussion and no comment. Okay, so you need to act and comment into what you summarize.
I think for the discussion, maybe you can conduct the experiment and all the experimental details and not just try to like some last point they can point out, try to raise some of your opinion. Yes.
Okay, so that can sum up the game. Okay, so thank you very much.
Okay, so I would like to invite all the reporters to come up here. I will need to save your presentation slides. Alright? And please leave the laser pointer and the pen on the table. And for the teachers, please leave your name card and your grading slides on the table. Thank you.